What's up, everybody? Welcome to lecture 22 over section 4.3. I just want to clarify a mistake that I think I have made in the last three lecture videos. In the three different parts of lecture 21, I was going over section 4.1 and 4.2. I saw I had a typo when I made the titles. I said 4.1 to 4.4. It's actually 4.142. I may have said that in the lecture videos as well. I don't remember. I don't honestly know at the moment. So if I did, that was a mistake. It was supposed to be 4.1 and 4.2. That said, this lecture 22, is over section 4.3, which you can find at the end of the notes of 4.1 and 4.2. It's all over what's called the fundamental theorem of calculus. The fundamental theorem of calculus, the way the book presents it, I personally think should be presented backwards. I think you should start with part 2 and then part 1. So I'm going to present it that way here. That's why we have the fundamental theorem of calculus part 2 first, because I think that's going to help make things a little bit more clear down the road. And it just flows better. I personally think, as far as what we just learned to where we're going, this has a better flow to it. So, with all that said, we'll start off with this question. Given that the derivative of capital F of x is equal to lowercase f of x, what's that definite integral? The definite integral from a to b of, lowercase f of x. What is that? Well, that's where the second part of the fundamental theorem of calculus comes in. It tells us that given lowercase f of x is equal to the derivative of uppercase f of x, and that f of x is continuous on this closed interval from a to b, then something nice happens. The definite integral from a to b of lowercase f of x with respect to x is equal to capital F evaluated at a, evaluated at b, minus capital F evaluated at a. And just to condense this notation a little bit, we oftentimes like to write capital F of x from a to b. So sometimes, just to abbreviate this notation, we'll use this bar, this long bar, just to say we're evaluating f at b and subtracting from it f evaluated at a. So this is really nice, because what it does for us is it lets us avoid all of what we just did in that last lecture. It lets us avoid that series development, which is great because, well, as you saw in part 2 of that video, that's long, it's arduous, and a real pain in the ass. I mean, if we're being honest about it, right? And this is where the second part of the fundamental theorem of calculus is a real godsend. It comes in and it lets us get rid of that series evaluation and instead just say, well, if I know that antiderivative, or an antiderivative of f of x, lowercase f of x that is, then all I have to do is evaluate it at the upper bound and subtract from it that same antiderivative evaluated at the lower bound. Now, just to see this in action, we had seen in lecture 21 that the integral from 0 to 3 of the function x cubed minus 6x integrated with respect to x is equal to negative 27 over 4. I actually got it to a place where it was like 81 over 4 minus 27 or something like that. So there was a little bit more work that had to be done, but this is what it comes out to be, is negative 27 over 4. Now we're going to use this fundamental theorem of calculus to evaluate this expression. Okay, well, before we do anything else, we're going to act like these bounds aren't here. We're going to ignore them for a second. So we're going to just evaluate x cubed minus 6x integrated with respect to x. We're going to hold on to those bounds from 0 to 3. Well, we know that this thing, when we evaluate it out, is going to come out to be 1 over 4 x to the 4th minus 3x squared. And we're going to, my mistake, plus a constant. As I've said before, everybody forgets those constants. Everybody does. So learn from the rest of us. And don't forget your constants. So plus that constant. And in a second, we're going to see that that constant just disappears. Which is really nice because that means you can integrate this thing, not worry about the constant, and then just evaluate it at the bounds, take the difference, and you're done. Which is really nice. So, we've got 1 over 4 x to the 4th minus 3x squared plus c. We're going to evaluate that at 0 and at 3 and then take the difference, right? So, expanding this all out. This first set of our first evaluation is going to be at 3. So we're going to have 1 over 4 times 3 to the 4th power minus 3 times 3 to the 3rd, or 3 to the 2nd power plus our constant. And then from that, we're going to evaluate all of this at 0 and subtract, right? Well, this first term is going to be 0, the second term is going to be 0, and all that's going to remain is our constant. So now, doing the rest of this, 3 to the 4th power, well, that's 9 squared. 9 squared is 81. So we have 81 over 4 minus 3 squared is 9 times 3 is 27 plus a constant minus a constant is equal to 81 over 4 minus 27. In other words, it's just the antiderivative evaluated at your upper bound minus the antiderivative evaluated at your lower bound. If you want to go in and check, this does in fact come out to be negative 27 over 4. That was where we left off in part 2 of lecture 21. But the point of all of this is to say, all you have to do is evaluate that antiderivative, then calculate what that result is at your upper bound and subtract from it what that result is at your lower bound. And that's it. That's all she wrote. In other words, we could have skipped over these constants. It would have ended up at the exact same place. So having said that, let's check out a couple more examples. All right, so we're gonna run through all three of these pretty quickly. Start off with, we're gonna look at this e to the x here. The first thing we wanna do is we wanna pull off our bounds, right? Just kind of pull them off to the side and hold on to those for later. So for that reason, and just to introduce some new notation, one of the things mathematicians will oftentimes do is use square brackets to denote the same thing that that bar was doing, right? And the reason why we're using square brackets here is just so we can say we're applying it to all of this, right? So to show you what I mean, here we're going to have the square bracket being open. We're going to have the integral of e to the x dx. Then we're going to close that square bracket, and we're going to pin our bounds back onto it. So nothing really too exciting there. We're just using the square brackets because it's a good way of showing we're going to apply these bounds to everything inside. So from here, we're just going to evaluate this. Well, this is going to come out to be, this integral that is going to come out to be e to the x plus a constant. But that constant's going to wash out in a minute, so we don't really need to write it. Excuse me. I am just putting it here so that we remember it insofar as the indefinite integral is concerned. But really, like I said, we don't need it in this case because it's going to get washed out in the end no matter what. So this is from 1 to 3, and now we're just going to evaluate e to the x at 3 and subtract from it e to the x at 1. And that's it. That's all there is to it. Now moving on to this cosine example, well, we know that the indefinite integral of cosine of x is sine of x plus a constant. So the definite integral is just going to be sine of x evaluated from 0 to 2 pi. And this comes out to be exactly 0. Oh, wait a minute though. That's supposed to give me something about area, right? And I know the graph of this thing looks something like this. So if this is supposed to be the graph, and I clearly have all of this for area, how the hell is this definite integral going to give me 0? Well, it's because this is calculating what's called the signed area, remember? And what happens is that this area is equal to, but opposite of, this area. So the two areas just cancel each other out, and you end up with an area of 0. So having said that, I should say a sine area. So having said that, let's imagine I ask you to find the proper area between cosine of x. Oh, I misdrew this. Sorry, everybody. I just realized I misdrew that. We're integrating cosine of x. So the area, or rather the graph, is this one. And again, these two areas are exactly opposite of this area. These two signed areas are exactly opposite of this signed area, and that's why you get that cancellation. But if, on the other hand, I ask to find what the exact area is, the proper area between our function and the x-axis, what would you do? Well, you would take these two pieces, add them together, and then instead of using the negative of this, you would just take the absolute value, right? And add all of that together. And we'll talk more about this in lecture 24, I think. But I just wanted to give you all a taste of that particular type of thinking, right? This is evaluating the signed area. So for that reason, this little bit has negative area. This top bit and this top bit have positive area. And it just so happens that the sum of those signed areas comes out to be 0. Now moving on to this other example. All we're going to do here is, again, pull our bounds off to the side, evaluate that indefinite integral, which is going to come out to be the ln of the absolute value of x. Our bounds are from 3 to 6, so this is going to be the ln of 6 minus the ln of 3, which is equal to the ln of 2. So that's all. Pretty quick and easy, actually. A lot better than having to use those series, right? All right, so let's check out the first part of the fundamental theorem of calculus now. So the first part of the fundamental theorem of calculus, what it tells us is that we've got this function f, and it's continuous on the closed interval from a to b. Then what we could do is define another function g of x on that same closed interval, a to b, and is differentiable on the open interval a to b with the derivative f of x by setting that function g of x equal to the integral, the definite integral from a to x of f of t with respect to t. So effectively, all we're doing is we're integrating f of t between two bounds, but we're just saying one of those bounds is a variable, right? Now this has some implications for us, in particular here. We're going to look at that in this example that I'm going to write up in just a second. Well, I guess not in just a second for y'all. I'm going to write up the first example now. Now, in this first example here, fundamental theorem of calculus lets us just calculate it directly. In fact, it's not even hard to calculate it directly. It is quite literally as simple as saying, well, we know that g of x is equal to the integral of all of this, right? This is our f of x. And we know that g primed of x, or rather, I'm going to say this is our f of t. And we know that g primed of x is equal to f of x. So that tells us g prime of x is equal to 1 plus the square root of the quantity 1 plus x squared. That's it. That is that easy. Yeah. Now the second one, on the other hand, takes a little bit more finagling. The second one, we need to use the chain rule. We need to start by saying that this is equal to Well, first, before we do anything else, we need to define what u is. We're gonna set u equal to x to the fourth. In which case, this is equal to dy, du, du, dx, where dy dx is equal to, dy du rather, is equal to d du of the integral from 1 to u of secant of t dt times du dx. Well, we know u is equal to x to the fourth, so that's going to come out to be 4 times x to the third. And the secant, all that, is just going to come out to be secant of u. So we have secant of u times 4 times x cubed. And finally, we started by saying u was equal to x to the fourth. So we have secant of x to the fourth times 4x cubed. That's it. So it's just an application of chain rule. Having said all that, that's all I got for y'all in this lecture. If y'all have any questions, of course, swing by office hours as usual. Yeah, have a good one, everybody.